In this video we are going to explain cascade form IIR filter realization structure. Cascade form IIR filter realization structure. Okay, here let us consider IIR filter system function as h of z, that is a product of individual system functions like h1 of z, h2 of z and so on, hk of z. So that means here consider one h of z system function and then split this system function into the product of the individual system functions. These system functions are either first order or second order. First order filters or second order filters, and then realize these individual system functions either with the direct form 1 or with the direct form 2 as discussed in earlier, right? Okay, so that means here if you observe the block diagram here for this, for a system h of z, here input is x of n, output is y of n. If you decompose this system into h1 of z, h2 of z, h3 of z and so on, hk of z, if these are connected as like a cascading form like this, then this h of z is nothing but h1 of z into h2 of z and so on, hk of z. It becomes like that. That means here h1 of z output is assume y1 of n, h2 of z output is y2 of n and so on like that. So here h1 of z is nothing but y1 of z by x of z, h2 of z is nothing but y2 of z divided by y1 of z and so on. In this way, here if you multiply all the individual transfer functions like this, and so on, here y of z by y k of z, assume like that. Okay, so all these values are gets cancelled. Now we can get y of z divided by x of z, that is nothing but h of z. That means cascading form of connection is nothing but when you cascade all individual blocks like this. So here these corresponding system functions are multiplied to get the overall transfer function of the system. Hence that is h of z is equal to h1 of z into h2 of z and so on, hk of z. Okay, so here cascading form is nothing but multiplication or product of the individual either first order or second order system functions system functions. Okay, now here for example, if you consider these individual transfer functions are second order filter transfer functions, they can represent like bk naught plus bk1 z inverse plus bk2 z power minus 2 and into bm0 plus bm1 z power minus 1 plus bm2 z power minus 2 divided by 1 plus ak1 z inverse plus ak2 z power minus 2 1 plus am1 z inverse plus am2 z power minus 2. So okay, here if h of z is like this, so I just split this h of z into two system functions. One is the h1 of z and the other one is the h2 of z, where h1 of z is nothing but the first one bk0 plus bk1 z inverse plus bk2 z power minus 2 divided by 1 plus ak1 z power minus 1 ak2 z power minus 2. Similarly, h2 of z is nothing but second one. Like this. So implement each one, right, with either direct form 1, direct form 2. Which one is better? Direct form 2. So in this case, the number of memory units are less. That's why. So here I am using direct form 2 structure. Based on that, here simply remember numerator. Remember how can we easily draw the direct form 2 structure? By using this h of z form like this, right? Numerator polynomials are there, denominator polynomials are there. So numerator polynomial coefficients are bk0, bk1, bk2, denominator ak1, ak2. So here, so simply first draw number of delay units. How many? 2 here. That means here z power minus 1, here z minus 1. So now here use the summers, adders. Here also first place adders. Now, so here right side use the numerator polynomials. So here bk0, bk1, here bk2. So in this way we can simply finish the structure here like this, and then left side use the multipliers like this, ak1, ak2, and put the sign inverse of this sign. Here is a plus, use the minus sign. Here if here is a minus, use here plus sign. That means opposite sign, minus ak1 minus ak2. So now connect like this. Here x of n. So this one is for, so use the dotted lines, right? This one is for h1 of z. Okay, so then here output is fed to the h2 of z input, h2 of z system input. Now again here do the same realization structure. So that means firstly place delay units, Z inverse, Z inverse. Now place multipliers Bm0, Bm1, Bm2. Here minus Am1, minus Am2, and then add all these values. Then here this is the output. That means in our example we have taken only two terms, two products here, like H1 of Z, H2 of Z. So now we implemented these two, H1 of Z and H2 of Z, using direct form 2 structure, and then cascade these two transfer functions like this. Then the realization is completed in a cascading manner. So such that it is called as cascade form realization structure. Okay. Then here coming to the another one, parallel form realization structure. Right, in the cascade form all the system functions are in series way connected. Here parallel form means, here observe how can you realize the system function. See here parallel form means just take the partial expansions, partial fraction method. If h of z is there for IIR filter based on partial fraction expansion method, just expand the h of z. So that h of z is nothing but, maybe for example it may be in the form like some constant plus summation of individual system functions. Here constant means here partial fractions are applied for the functions, rational functions, like if numerator polynomial order and the denominator polynomial order. Numerator polynomial order should be less when compared with the denominator polynomial order. If our h of z is not in that form, so first we should do the division, and then so you have to extract the form like numerator polynomial order should be less than denominator polynomial order. Until to reach that particular form, we have to divide the original rational function h of z. Okay, that's why here in such a case you may get the c, right, constant value here. So otherwise, so here c is 0. Okay, now and after getting the after dividing, you can get the one rational function here. So numerator polynomial divided by denominator polynomial. So now based on the partial fraction method, you just split and then extract the formation like this. That means c plus h1 of z plus h2 of z plus and so on hn of z. Okay, like this. Here h1 of z or almost those are nothing but single pole systems, otherwise single order, first order systems, right? So if the particular here h1 of z, h2 of z, any one of the particular system function is having complex values, then it must be in the second order form. That means here also these functions either in single order form or in second order form. And of course, realize these systems, individual system functions, with either direct form 1 or direct form 2. Direct form 2. So now here, if it is a single order system, it may be in the form like Ck by 1 minus Pk z power minus 1. If it is a second order form, this is Bk naught plus Bk1 z power minus 1 divided by 1 plus Ak1 z power minus 1 Ak2 plus Ak2 z power minus 2 in this form. Okay, right? So general forms, if it is a single order system, it may be in this form. If it is a second order system, it may be in this form. Okay, right. So now after realizing these hk of z's either with the direct form 1 or direct form 2, so it may look like this. Okay, now here is a x of n input, c is nothing but multiplier, and realize the individual functions here either with direct form 1 or direct form 2. So h2 of z and so on. hk of z, and then just add this c with this h1 of z, then add this resultant one with the h2 of z, and here finally add all this, then you can get y of n. You can get y of n. That means y of n is nothing but c plus h1 of z plus h2 of z plus and so on hk of z. In this way we can realize any IIR system with the parallel form. Okay, so remember, parallel form means we have to use the partial fraction expansion method. Firstly, do the division until to get the numerator polynomial order should be less than the denominator polynomial order. After dividing, then do the partial fraction. So here we may get the single order systems or you may get the second order systems based on the direct form 1, either direct form 1 or direct form 2, realize these individual structures. Okay, and then finally in this way connect, okay, to get the y of n. Okay, thank you.